So sometimes we need to make inferences about the population variances. And so to do that, we will do the goodness of fit test using chi-square. A variance can provide important decision-making information. So consider the production process of filling containers with a liquid detergent product. The mean filling weight is going to be important, but also is the variance of the filling weights. So by selecting a sample of containers, we can compute a sample variance for the amount of detergent placed in a container. If the sample variance is excessive, overfilling and underfilling might be occurring even though we have a correct mean. A goodness of fit test is one of the most commonly used statistical tests. And here in the table, we have the historical relative frequency distribution of policy types for an insurance firm. So we would consider these values to be our expected frequencies. The purpose of this test is to compare an observed frequency distribution to an expected frequency distribution. The scale of measurement will be nominal. So each of our categories, so in the case of Bubba's Fish and Pasta, would be chicken, fish, meat, and pasta. Those are also sometimes referred to as cells. So here we have a survey of 120 adults. If the entrees are all equally popular, we would expect to see 120 adult sampled divided by 4 categories to get 30 adults per entree. And so that would be our expected frequency. To investigate, we can use the 6-step hypothesis testing procedure. The null hypothesis is that there is no difference between the observed values and the expected values, and any differences that are seen would be due to maybe sampling error. The probability is 0.05 that a true null hypothesis is rejected. The test statistic follows the chi-square distribution, designated with the symbol chi squared. And so in this example, we have 3 degrees of freedom. The way we find degrees of freedom is k minus 1, where in this case k equals 4. So to find the critical value, we would go to a chi-square distribution table and find that the critical value is 7.815. And we can find that by locating 3 degrees of freedom in the left margin and then moving horizontally and reading the critical value in the 0.05 column. So on the next slide, we're actually going to conduct the test. So here we have the formula for the chi-square test statistic. F naught is the observed frequency, and F sub E is the expected frequency. So basically, once the observed frequencies and the expected frequencies are listed in columns, you can subtract the expected frequency from the observed frequency in the next column. Then you square that difference and finally divide the squared difference by the expected frequency and sum the results. This sum that you get is the chi-square statistic. Here we do not reject the null hypothesis. We're going to conclude the differences between the two observed values, and the expected values are going to be due to random chance. The chi-square distribution has many applications in statistics. Sometimes it's used to characterize data sets and statistics that are always positive and typically right skewed. Notice how each time the degrees of freedom change, a new distribution is formed. So if we look at the chi-square distributions for selected degrees of freedom, we see that they have slightly different charts. So remember, a normal distribution has 2 parameters, mean and standard deviation, that are used to describe its exact characteristics. The chi-square distribution just has the one parameter called degrees of freedom, which influences the shape, center, and spread of the distribution. The chi-square test can also be used if the expected frequencies are not equal. So here we have an example that gives a practical use of the chi-square goodness of fit test, namely to find whether local experience differs from the national experience. So we can use the AHAA information to compute the expected frequencies for the Bartow Estate residents. If there's no difference between the national experience and the Bartow study, then the expectation is that 40% of the Bartow residents would have been admitted once. So we get that by zero point 0.4 times 150 to get 60, and so on. So the observed and expected frequencies for Bartow residents are given in the table here. And the next slide, we're going to go into the 6-step hypothesis test. So you're going to use the chi-square distribution table and the 0.05 significance level to find the critical value for the decision rule. The number of degrees of freedom here is 3, which was found by k minus 1. So k is going to equal 4. The critical value is 7.815. And so our decision rule is to reject the null hypothesis if the chi-squared statistic is greater than 7.815. The chi-squared statistic is 1.3723. So we failed to reject the null hypothesis and conclude that there is not a difference between the local and the national experience for hospital admissions. When there is a small frequency in a cell or category, it results in too much weight being given to those categories. So when possible, we combine categories to resolve that problem. In this example of levels of management, we have 3 vice president cells that ended up being combined to create an expected frequency of 7. Here are the steps to perform a goodness of fit test to determine whether a sample of observations is from a normal population. Once all the expected frequencies have been calculated, you put them in a table in the column for area. The areas should all add up all to 1.000. So now we can combine our classes of our expected values that are less than 5. And once that's done, we're going to continue with our chi-square statistic analysis and go into our hypothesis testing. So now we have our hypothesis test. When we estimate population parameters with sample data, we lose 1 degree of freedom for every estimate. So the number of degrees of freedom is k minus 2 minus 1, which gives us 8 minus 2 minus 1 equals 5, since we use the sample mean and the sample standard deviation. So from the chi-square distribution table, using the 0.05 significance level, the critical value is going to be 11.070. So using our chi-squared calculation, we can determine that the chi-square test statistic will be 5.220. So do not reject the null hypothesis because it appears that the distribution of profits would be normal.